Hello everyone, today we are going to talk about natural exponential function. And first we are going to start with definition of a very special number base of natural logarithms, also known as number e. Well guys, I'm going to define it like mathematicians define it. Number e is defined as a limit, as a limit as n goes to infinity of the expression 1 plus 1 over n to the power of n. If you look at this expression, kind of not very difficult to understand what is limit. A limit is the idea of bringing something to a very, very large number here. So I'm going to show you like how the limit can be calculated and why actually we don't give the definition as just a number. Imagine that you set up n equals to 1. What is going to be then e? Well, then e is going to be approximately 1 plus 1 over 1 to the power of 1, which is going to give you what? 2 to the power of 1 is 2. Now you start increasing n because somebody tells you that we need to bring n to infinity and gets 2 here. E approximately is going to be equal 1 plus 1 over 2 to the power of 2, which is going to be 1.5 to the power of 2, which is going to give you 225. You see that number is changing a little bit, increasing, right? Now I'm going to consider n, I'm going to skip some n's and consider n equals 10. E will be approximately equal, 10 is closer to infinity, right, than 1. 1 over 10 to the power of 10, which is going to give you 1.1 to the power of 10, or it's going to be approximately 2.593. You see that number is getting bigger. Well, let's skip some more numbers and take 100. 100 is even closer to infinity. 1 over 100 to the power of 100. We're going to have 101 to the power of 100 and approximately equals 2.7048. Well, we can continue the process and eventually, guys, you see that you are going to see that digits are not going to change the whole number. Like, for example, for the first like 1, 2, 3, 4 numbers here, the only 2 was not changing, right? But eventually 7 stops changing, and then it's going to be instead of 0, 1, which is not going to change. So I'm going to write down what is going to happen when n goes very large. E will be approximately equal to 2.7, like same two numbers, 1, 8, 2, 8, and there are going to be infinitely many digits actually. Well, number is a special in math because it describes lots of natural growth in like almost everywhere. So we are going to return back to why we define it such a strange way. But for now, just kind of trust me that number e, it's a special number which is equal to 2.7 and some other digits. Remember number pi. Number pi is going to look like this: 3.14, 15, and more digits. You also don't need to know the whole number, right? And you also know that number is going infinitely far away. It has infinitely many digits. Actually, both numbers are not only rational numbers, which means that they kind of cannot be represented as a fraction of two integers, but they are also transcendental numbers. So they are even not looking like a square root of 2. They're even more complicated. Well, for now, guys, we just need to know that e is approximately 2.7 or approximately 3. By the way, guys, e is approximately 3, but less than 3. And pi is approximately 3, but greater than 3, right? Let's graph this because the idea is to talk about exponential function. So exponential function is f equals e to the power of x, exponential function. Going to graph it because e is approximately 2.7, that's greater than 1. The graph is going to look like my first graph I was graphing, right? So it's going to be 1 at 0, and 2.7 is approximately 3. So the next point is going to be here, and the graph is going to look like this. That's e to the power of x. 2.7 at 1, and this is 1, and this is x, and this is 1. Horizontal asymptote. E to the power of negative x is going to be a reflection, right? And I'm going to graph something like a similar over here. Let's change the color. Reflection of this one, right? All these points are going to be reflected over here. Okay, and basically, guys, same transformations can be applied to exponential functions. So if you want to move it up or down or left or right, you can do it like normal, normal 2 to the power of x. How are we going to use this exponential function? For now, guys, we are going to use it to extend a little bit our formula for compounded interest. Return it to compounded interest. Well, guys, here I'm going to prove something, but if you don't understand it, you just kind of memorize the formula. Actually, the formula we are going to have is going to be easier. So remember that we have a principal, we have interest rate, we have also n times per year. The interest is combined. And we can have t number of years. I'm going to put everything into one formula, and just recall the formula is I over n, right? And here n t. And what I'm going to do here, guys, I'm going to do a little substitution here. I'm going to introduce a new number m, which is going to be n over I. So for example, this one is 1 over m, right? So I'm going to modify my formula now. Principal 1 over m. And here, instead of n from here is equal m I t, right? I'm going to write down m I t. Sorry, no, there is no t here, but t over here. M I. Well, now guys, I'm going to put I and t outside and write down p 1 over m to the power of m, and this one goes to the power of I t. Well, because when we multiply powers, when we multiply exponents, we actually raise it power to the power, right? Well, guys, what is going to happen when we combine interest not like quarterly or annually or semi-annually, but every day or every second? Well, our m, number of times we combine, which is like m, n over I. This one will go, if we bring it to infinity, then this one will go to infinity too, because infinity divided over a number is infinity. But we remember that this one, this expression, when m goes to infinity, let me remind you, it's over here. Well, here it's in terms of n, is equal to number e. So I'm going to just write it down. It's p, e, and the power is I t. And that's a new formula. And you see that new formula is much better than compounded interest formula. This interest is compounded continuously because we are bringing the number of times we combine our interest to infinity. So we combine it every second, every millisecond, every nanosecond. So this is called continuously compounded interest. Well, formula looks much better than like just compounded interest, right? Let's use this formula for the problem we had before. So for example, I'm going to write down the problem. Principal is 2,000. Interest rate is 4%. T is 5 years. Before, we needed to know how many times you combine it during a year, right? Quarterly, for example, we had question about quarterly combinations. But now, because the number of times goes to infinity, it disappears from the formula. And to calculate A, we just need to plug in just three numbers we know from here, 2000. And over here, sorry, should not be parentheses, should be e to the power of interest rate, which is 0.04 rate. We remember that we kind of convert this into the parts of unit, multiplied by time, which is 5 years. We're going to have 2000 e to the power of this one by 5 is going to give me 0.2. Guys, give me a second. I'm going to use my calculator and calculate this new number, just to compare to the number we had before in the lecture before, when we were combining this interest quarterly. Let me see. So e to the power of 0.2 multiplied by 2000, and I have 2442.81. Well, approximately. Actually, we have more digits, but we cannot collect like less than 1 cent, right? Now, guys, I don't know if you're going to see or not, but I don't really remember what we had quarterly. So this is the answer on account after 5 years if you do it continuously. Let me try to see what we have if we do it quarterly. I'm going to go to the previous page just to show what is going to happen when quarterly. Yeah, where is my? Yes, almost. I'm trying to go back to the problem. So guys, when we did it quarterly, it was this number, 2,440 and 38. Let me write it down somewhere so I can compare it to this number, 2,440 and 38. Now let's go back to our problem. So that was kind of the problem when we combined it. Sorry, kind of. This one. Sorry, I'm trying to get to my whiteboard and I changed it. So okay, now I'm going to write down like what we had before. 2,440, 38. This is quarterly. It's 4 times a year. Well, you see the difference is not very big. It's just like $2.81 here and $0.38 here. But it's still, you see that continuously is going to give you slightly bigger. Yes, for 2000, the difference is not essential, but for like larger numbers, it's going to be more essential. Okay, well, that's all about exponential number, and just do your homework. Okay.